Myself, Minu Joske, Assistant Professor, Mathematics Department, Jodhi Engineering College. Today, we are going to discuss the topic Fourier transform. So, first of all, we will discuss some introduction regarding this Fourier transform. We know this Fourier series actually represents the periodic function as a sum of sinusoids. Now, this Fourier transform has wide application in the field of astronomy, signal processing, linear time invariant system, etc. And the detail we will study in the coming years of this B.Tech. We will discuss the formulas regarding this Fourier transform and the inverse Fourier transform. Fourier transform of f of x when this x is between minus infinity and plus infinity is denoted by f bar of lambda, also denoted by f of x. We read it as Fourier transform of f of x, which is equal to 1 by root of 2 pi integral minus infinity up to plus infinity e raised to I lambda x f of x dx. Also, the inverse Fourier transform of f bar of lambda, or the inverse Fourier transform, is represented by f of x, which is equal to 1 by root of 2 pi integral minus infinity to plus infinity e raised to minus I lambda x f bar of lambda d lambda. So Fourier transform is represented in terms of, or in the form f of x, while the inverse transform is represented in terms of f of x. Now we have the Fourier sine transform. Fourier sine transform is denoted by fs bar of lambda, or it can be denoted by fs of f of x. Fs of f of x is equal to root of 2 by pi integral 0 to infinity f of x into sine lambda x dx. Also, we are having the inverse Fourier transform. Inverse Fourier sine transform is represented by f of x root of 2 by pi integral 0 to infinity fs bar of lambda sine lambda x d lambda. This is the formula for the inverse Fourier sine transform, and this is for the Fourier sine transform. Similarly, we are having the Fourier cosine transform. Fourier cosine transform of f of x denoted by fc bar of lambda. Another notation fc of f of x. We read it as Fourier cosine transform of f of x, which is equal to root of 2 by pi integral 0 to infinity f of x cos lambda x dx. And the inverse Fourier cosine transform is fc bar of lambda is represented by f of x, which is equal to root of 2 by pi integral 0 to infinity fc bar of lambda into cos lambda x d lambda. So the difference between the Fourier transform and the sine and cosine transform is that for the Fourier cosine and sine transform, other than the integrand, we will have the constant as root of 2 by 5. But for this Fourier transform, we are having it is 1 by root of 2 pi. And again, for this Fourier transform, both this Fourier transform and the inverse, the limit will be from minus infinity up to plus infinity. But for this Fourier transform and the inverse Fourier sine transform and the inverse Fourier sine transform, it is from 0 to infinity, as in the case of Fourier cosine and its inverse. So we need to by heart all the 6 formulas for doing the problems of this topic. So by heart the formulas of this Fourier transform, Fourier in sine transform, cosine transform, and its inverses. Let us have some look on the problems on the topic Fourier transform. Let us discuss the first topic as Fourier cosine transform. Find the Fourier cosine transform of f of x is equal to x 0 less than x less than 1 equal to 2 minus x 1 less than x less than 2 and equal to 0 when x is greater than 2. So this functional value of f of x is divided into 2 from 0 to infinity. From 0 to 1 it is given as x, 1 to 2 2 minus x, and from 2 onwards it is given to be 0. We need to find the Fourier cosine transform. So that first write the formula for the Fourier cosine transform. Fc of f of s is equal to root of 2 by pi integral 0 to infinity f of x into cos lambda x dx. And since the function f of x takes three different values in the three intervals, we will split this integral 0 to infinity into 3. First is from 0 to 1, second from 1 to 2, and third from 2 to infinity. And in the integrals, the function takes the values x, 2 minus x, and 0 respectively. So we could see the last integral becomes 0 and remains the first and second integral. So we need to evaluate this both the terms. So while evaluating this the first term, we need to apply the rule integration by parts. So let I take this x as the first function, cos lambda x as a second function, so that the rule is like this: first function into integral of second. So first function is x into integral of cos lambda x is sin lambda x by lambda minus derivative of first function, derivative of x, and it is 1. 1 into integral of the sin lambda x by lambda, and the integral is minus cos lambda x by lambda square. So initially for the integral, we are having the positive sign, and then it becomes a negative sign. Alternatively, next term will have the positive sign, etc. So the rule is like this: first function into integral of second function minus derivative of first, integral of second, derivative of first, integral of second with the alternate sign, etc. So then for the next term, we should have the derivative of 1, and we know derivative of 1 becomes 0. So we stop the integration and we will replace the limit from 0 to 1. Same rule for the second integral also. First function 2 minus x, integral of cos lambda x sin lambda x by lambda minus derivative of 2 minus x, and it is equal to minus 1. Integral of sin lambda x by lambda, which is equal to minus cos lambda x by lambda square. And then next we will have the alternate sign positive. Next comes the derivative of this minus 1, but we know derivative of the constant term is equal to 0, so that we could stop the integration and the limit from 1 to 2. Now we need to replace the limits of the integral. Upper limit for the first term, upper limit is 1, lower limit is 0. For second term, upper limit is 2 and lower limit is equal to 1. So when I apply the limit, I will apply the first upper limit first, so that I should replace as every x is equal to 1. Now before that, if I combine these two minus signs, the middle term becomes positive. That actually it becomes positive, minus into minus getting plus sign. Now take this x is equal to 1, so that when x is equal to 1, it will be 1 into sine lambda into 1. That is equal to sine lambda divided by lambda. Now it is actually positive sign, plus cos lambda into 1. Cos lambda into 1 becomes cos lambda divided by lambda square. That means we have replaced the upper limit in the term. Now we need to replace the lower limit. So we know before replacing the lower limit, we should take the sign as a negative. So minus of. Now replace x is equal to 0. So it is 0 into sine 0. 0 into sine 0 is equal to 0. That means I am not writing that term. I am not writing the term 0. And then for the second term, cos lambda into 0, that is it becomes cos 0. Cos 0 is equal to 1. So it is 1 by lambda square, the negative sign of the lower limit. So it is minus 1 by lambda square. Now for the second term, upper limit becomes 2. So it is 2 minus 2. 2 minus 2 is equal to 0, which means when I replace the upper limit, the first term vanishes. And the second term, totally this will be negative sign. Minus into minus becomes minus sign. Now upper limit becomes cos lambda into 2. It becomes cos 2 lambda divided by lambda square, minus lower limit is equal to 1. 2 minus 1. 2 minus 1 is equal to 1. So 1 into sine lambda into 1 divided by lambda, and that is equal to sine lambda with a negative sign. Actually, this takes the negative sign, but we are having one more negative of the lower limit, so that when I replace this one, I should have this positive sign. So plus cos lambda into 1, cos lambda into 1 is equal to cos lambda divided by lambda square. So that if I look at the term, sine lambda by lambda and minus sine lambda by lambda can be cancelled. Now cos lambda by lambda square and then cos lambda by lambda square can be added. So it is 2 cos lambda minus cos 2 lambda minus 1 divided by lambda square. Hope the problem of this Fourier cosine transform is clear. We will continue in the next session. Thank you.